So I just wanted to welcome everyone to the Andlinger Center Highlights Seminar. I am Daniel Sigmund. I'm a faculty member in the Department of Geosciences, and I am up here introducing Jess because I represent his roots. So Jess is a geochemist, a chemical oceanographer, and a paleoceanographer, a paleoclimatologist. And there, people will say that people have worked on many things. In Jess's case, it's just sort of unavoidably true. It could even be an insult how many things he's worked on. But there has been one through line, or multiple through lines, but one major through line in his work has been his work on the carbonate chemistry of the ocean, specifically calcium carbonate in the marine environment. And the starting point for that with him, more or less, was on his work on deep sea corals and trying to use them as a paleoclimate and paleogeochemical archive, a way of reconstructing, for example, CO2 storage in the deep ocean. But in doing that work, Jess had to delve into the way that biomineralization occurs in these systems, and became a leading expert in carbonate biomineralization as a result of that. But this work started to introduce him, well, he knew all along, but it got him closer and closer to another area of research, which is how calcium carbonate dissolves in the ocean. So the ocean's really interesting with respect to calcium carbonate cycle. It's super saturated in surface waters, and organisms take advantage of that as a starting point for the biomineralization they conduct. But in the deep ocean, calcium carbonate is undersaturated. But it's always been a critical question how rapid calcium carbonate dissolution can occur for a given level of undersaturation. And this is particularly important in the context of well, it's important in the past, but it's also important in the context of ongoing CO2 inputs to the atmosphere, where CO2 is entering the ocean, and when it enters the deep ocean in particular, it can drive calcium carbonate dissolution, and the question is how quickly. Anyway, Jess saw this field that has been around. I was going on cruises back in the 1990s due to my advisor really working in this area of trying to understand what controlled the rate of calcium carbonate dissolution on the seabed. And Jess, sometime later, this stuff really never got resolved, and was a huge hole in our research area. And Jess started a large research area to try to improve on that. And it took him somewhere weird, and into this room. And so, in the context of, so this is a carbon disposal, what does CDR stand for?
Carbon dioxide removal.
No disposal in there, pal. Carbon dioxide removal approach that involves calcium carbonate reactions in the ocean. And I really I'm putting my money, I don't have any money, but if I had money, I'd put it on Jess. And there are a couple of reasons. One is this is an area where you really kind of need to understand the entire global carbon cycle to understand what is a true carbon sink and for how long. And in addition, as you'll see from the specific strategy that Jess is conducting, he's just the inherent technology and approach removes a lot of the uncertainty associated with whether indeed you're removing CO2 from the atmosphere. So with that, I should say that Jess has won a whole bunch of awards, which is true. I should also mention that, well, you're going to be hearing about this, that he's been working as the CEO for this company that he founded, Calcaria. But this is his story to tell you. So let's have Jess Adkins start his talk. Thanks, Jess.
Thank you, Danny. I really appreciate the introduction. Maybe even more so, it's terrific to get your good friends to be forced to say something nice about you, even though they don't want to, right? They really just want to tell stories about when I was too drunk sometime. So, and thank you for coming. I really appreciate it. Oh, that's good. I think whatever just happened there was better. I'm going to just kind of get into it here because I would like you to understand where we're coming from, and I would like to get your feedback on where we're coming from. This is work that is a joint collaboration academically for over a decade between me and Will Burleson at USC, a good friend of mine and now a co-founder of Calcarea. And then the other folks that you see here are Calcarea folks, Pierre being our third co-founder, and Melissa and Sitcha having worked on this in various ways. Sitcha mostly on the academic side. Okay, so how are we going to take, I'm sorry, I already screwed up. I should say something about this slide. Maybe. I love this image, right? This is a moment in time in shipping that is every single ship that has got its GPS turned on. It's awesome, right? Because you can see where the shipping lanes are. You can see that the ocean is somehow full of ships. It's not quite this full because, of course, the icons are a little bit too big for the scale here. This is a gigaton of CO2 emissions. This is 3% of our global emissions come from the fact that we don't make the things that we consume in the same place, and the cheapest way we've thought of to move stuff around is on very large ships. And so that's why this is about the same size as aviation. You might hear more about aviation and trying to decarbonize it, but it is just the same climate impact as aviation. And so that is one of the motivations for why you might want to try to figure out how to decarbonize the ships. Okay, we're going to decarbonize them using a mimic of a natural process. And you've probably heard that a number of different times, of people saying, oh yeah, we're doing exactly what nature does. And this is why we think it's what nature does, and it's what Danny was referring to about the overall cycle of alkalinity and carbon in the ocean. We understand, actually, what's going to happen to all of the fossil fuel CO2, or nearly well over 90% of it, because we understand what happens on tens of thousands of years timescale to the CO2 that comes out of volcanoes. It acidifies the surface ocean. We're seeing that right now. That's the other CO2 problem, ocean acidification. The overturning circulation carries that down to the bottom of the ocean, where the acidity hits the calcium carbonate, the base in the shells of the organisms that were made in the surface and fell down to the bottom. The negative feedback in the system to stabilize things is through the acid-base cycle, not through following the carbon atoms. This is something that is often, like, initially really hard to get your heads around. Like, why are we dissolving calcium carbonate in order to keep CO2 from being in the atmosphere? It's because the natural system, when you put CO2 out from volcanoes, doesn't get its carbon gloves on, like we've kind of designed a bunch of interesting systems to do, purify or trap that CO2, and then go find some place to store it underground, like some hole that you can stick it in. It is this perturbation to the acid-base cycle. The problem here, in terms of a natural, trying to use it as a engineered solution to our natural problem, is that it's this tens of thousands of year timescale. That doesn't feel like it's going to work so well for humans, and it hasn't been used in the industry for two main reasons, and I'm going to walk you through why we think we've jumped over both of these hurdles. The first is, we didn't understand, and Danny referred to this, the fundamental kinetics behind this reaction of CO2 plus calcium carbonate. That was just embarrassing to me and Will, and so we got started on the problem of how might this work without ever imagining an applied use for it. The second problem with AWL is that it needs lots and lots of water, and pumping water uphill gets expensive quickly, and so your life cycle analyses, your LCAs, get bad quickly. We're going to walk through both pieces of what we've done about that. So what about the dissolution rate side of it? What did we do, and what was sort of the context in which it was happening? Well, the first point is that the freshwater people really, they had their act together. Right? They understood this much better than those of us in oceanography did, and I'll show you what that all means. These are papers from the 70s, right? Where you're measuring, as a function of time, the pH increase when you drop calcium carbonate into the water. And so it's measuring the kinetics of this reaction of calcium carbonate dissolving into the water. And so the first little slope that you see here is the initial rate. all terrific, right? If you then go and now this plot is not versus time, but you think about what if I added some PCO2 to my system here, so didn't just let it be acid and calcium carbonate, but make the acid start to be carbon itself by adding carbonic acid or through CO2, then what you see here are a series of lines as a function of the hydrogen ion activity in the experiment. What was the rate? And the different lines are different concentrations of CO2. And so as a kineticist, what this tells you is that the hydrogen ion is really important for the fundamental attack of the surface to dissolve, but so is CO2. Right? And so if you wanted to work out a kinetic rate law, you would need to take both of those into account. And the community has done that. This paper came together much later than a lot of the data came out. This is the early 90s, but still, long time ago, Arakaki and Mucci wrote the definitive paper on the elementary reactions involved in a chemical rate law for the freshwater dissolution of calcium carbonate. And they wrote down the kinds of reactions you would have done too, right? What does it look like just dropping the solid into water in an undersaturated solution? That's got to be one of the pathways that happen, that you have a unit cell of calcium carbonate somehow going from being solid to being aqueous. We saw proton attack was important, right? That the rate scales very strongly with how acidic the water is. And so the protons attacking, this is now a representation of the surface carbonate ion concentration, the free carbonate ions sitting at the surface of the solid. That's what the little arrow here means. And then we saw carbonic acid was also important, and presumably that's attacking the calcium-free site that you see there. And so these three elementary reactions you can then put into a series of differential equations and model the whole system with these three, and you come up with the net rate here and the gross precipitation, the back precipitation that you see here. And so this plot is rate with both a precipitation side being negative and a dissolution side being positive as a function of this funny axis that I'll explain better in the next slide. But this is your percent distance from equilibrium. This is all the way away from equilibrium, and this is 80% of the way towards equilibrium over here. And you can see there's this strong curvature in both the data and in the model, and they've done a nice job of fitting it with these three elementary reactions. The reason that it took so much time, over a decade between the data collection and this model coming out, is we didn't understand the surface speciation, the chemical speciation of calcite in freshwater. What is the activity of the free calcium spots on the surface as opposed to the hydrated calcium spots or the hydroxylated calcium spots? Or is there a little magnesium that's in the seawater, in the freshwater that might be binding to the carbonate ion spots, right? That was Van Capellen's thesis that came out in the early 90s. And once we had the speciation of the surface, then Arakaki and Mucci could go work out the full rate law. And that flavor of speciation is going to be important to us along the way here as we go. So the folks in the freshwater had it all worked out. And yet we couldn't get our act together as oceanographers to do the same thing. And we had a very hard time describing the rate law or even measuring the rate law in the first place. And so what I'm showing you here is a log-log plot. Let's see, there it is. A log-log plot of rate versus this saturation state indice. And so what's going on here is we're defining an omega that is the ratio of where you sit the calcium and the carbonate ion concentrations relative to equilibrium, relative to the KSP. So if this number is greater than 1, you have a tendency to precipitate. If it's less than 1, you have a tendency to dissolve. And then we do 1 minus it and take it a log so that you have no idea what we're talking about, or it gets more confusing. This is 2% undersaturated. This is 10% undersaturated, and then this is infinitely undersaturated over here. So now we're close to equilibrium on the left and far from equilibrium on the right. And here's a bunch of data in the literature, both freshwater and seawater. And I plotted it in this funny way because this is where the ocean sits. So we had this real extrapolation problem of making measurements very far from equilibrium, and yet most of the ocean sits very close to equilibrium. And this led to a very empirical approach to coming up with rate laws, that you write down the rate as being proportional to the thermodynamic driving force. The proportionality constant is the K, It's then not even working, so you add an n as another fudge factor, and you can see that in the literature, n varied between 1 and 4.5. Oh dear. It can't actually have that variability, can it? Like, isn't there just sort of one rate law that's worked on? And there's orders of magnitude variability in the Ks that fit with these as well. So that's the problem that we got embarrassed by, that we said we can't tell you how quickly a coral is going to dissolve under ocean acidification because of this variability in the literature. And so we came up with a trick. It's Caltech, so it was an isotope trick because we're stuck in a rut about isotopes. And in this particular case, it turned out to be a pretty good idea. We take purely labeled C13 calcium carbonate, put it inside a gas impermeable bag, fill that up so there's no headspace in that bag, and change the pH or change the omega of this bag, and monitor the rate at which the C13-C12 ratio of the inorganic carbon in solution changes. And we become very sensitive because this is pure C13 adding to something where there's almost no there's only 1% C13 there to begin with. And so we get a very sensitive measure of the dissolution rate. And so a plot versus time of a measurements of the C13-C12 ratio phrased in this delta space or converted into the moles dissolved. Here are 4 separate bags, one very close to equilibrium, one further from equilibrium. And the measurement of the rate is just the slope on this plot. We don't have to have a conversion through pH or calcium and things that other folks had been doing previously. This turned out to be about 200 times more sensitive than what was out there. And we got to work. Here is a lot of bags, right? So each one of these dots is order a week, right, for running a bag. This is John Navio's thesis, where he worked on the temperature dependence of the dissolution rate. Same axes that I was showing you before, log of dissolution rate phrased as a flux here, right, as a real per area number, and log of the distance from equilibrium. And you dissolve more slowly when you're cold, and you dissolve faster when you're warm, okay? But maybe even more interestingly, N is suddenly looking like a function of saturation state itself, right? And they're very clear breaks in slope in these diagrams, and they're happening at about the same omega criticals, about the same undersaturation values, irregardless of temperature. There's even another one in here that's kind of hard to see, but because it's hard to collect points with just 1% away from equilibrium. But there's a real flattening off in some of the points here. We didn't have any data for the 21C ones at the time of this paper. And so there are these breaks in slope that are different ends depending on what saturation state you're at. Well, first of all, it really helped us in the ocean. We're now extending into the actual place where the ocean sits, and you can see immediately why the extrapolation from far from equilibrium was becoming such a problem, is that the curvature itself is changing as you come in towards equilibrium. And so there's something that N is very much less than 1 sitting down close to equilibrium, almost not even a function of the saturation state for the first 10% or so. Then there's this intermediate step, and then there is this very fast dissolution that is this canonical number that was sitting out there in the literature for the oceanographers of N of 4.5. Okay, so what's up with that? Well, we struggled with that for a long time of trying to figure out what was going on there. But we belatedly decided Patricia Dove, we should have been paying attention to her work much more closely. Patricia actually was a graduate student, I think, in the geosciences here at Princeton. This is work that came after she left Princeton. She was working on the dissolution rate of quartz. Very, like, whew, if the carbonates were hard, quartz is really slow, right? Like she was using AFM rather than the solution side, so she was looking to change the shape of the solid. But realized this really interesting and important piece of the theoretical side, which is that she could take classic nucleation theory, but BCF theory, and flip it on its head to explain dissolution. So nucleation theory to explain precipitation. What if we use those same energetic arguments to explain dissolution? And she pointed out there are really only 3 energetic modes that are available to do dissolution of solids generally. Close to equilibrium, you don't have enough free energy. You don't have very much free energy available from the chemistry of your water, And so you have to attack, you dissolve those things that are already pretty close to being dissolved in the first point. If you think about this as a collection of unit cells, this one is half dissolved. 3 of its faces are already in the water, and 3 of its faces are attached to the solid already. And so step edge retreat is the first energetic mode of how you would do dissolution close to equilibrium. If you go a little bit more acidic, or a little bit farther from equilibrium, then you begin to be able to open up etch pits in the surface at places where there's already strain in the solid, at defects that are already there. And then finally, if you add enough free energy to the system, you go even more undersaturated, you can begin to pluck etch pits out of homogeneous 2D surfaces. And that's the fastest you can go. Right? There's nothing, at that point, you've made 4 new step edges that are retreating, and your dissolution rate is really just about the frequency at which you nucleate the new etch pits. We loved this approach, right, because it explained 2 omega criticals, 3 different modes, the kind of thing that we were seeing in carbonate dissolution. And so we dug in a little bit into the theory. This looks like an absolutely horrible equation, and it kind of is, but it's easier to unpack than you might think. So this is Patricia's idea. This is when she worked out the energetic balance for these 3 different modes. What are the important terms that are there? It's a beast, but it's actually just on a plot of normalized rate over here on the left-hand side. That R is just the rate of dissolution. And as a function of the undersaturation, so that sigma is a version of the ln of omega, just to be different, this is a line on a particularly normalized plot. Right? If you have an intercept and a slope here, for whatever all these terms are. Well, a big chunk of these terms are stuff that you just know, right? They are the equilibrium saturation, the height of the step edge, the Boltzmann constant, the temperature, pi, right? Just constants or knowns of the system in the first place. And there are 3 terms that you want to keep track after you measure the rate and measure the saturation state. Beta is the velocity, is the step edge retreat velocity. This is, by the way, only for situations where etch pits are involved, either defect-assisted or homogeneous. NS is the frequency at which new etch pits are going to actually appear at the surface. That's probably going to be different for the defect one than it is for the homogeneous one. And alpha is the surface free energy, millijoules per meter squared, is sort of classic surface energy number. And you can see that the slope, right, the rate of dependence of rate on saturation really only depends on that free energy. The free energy of the surface goes up against the free energy available in the solution. Here's the free energy in solution. Here's the free energy of the surface. Okay, the intercept is dependent on the rate of retreat of the steps and of the nucleation rate. Okay, then very close to equilibrium, you end up with this kind of crazy equation. I'm not going to try to dig into it too much, except that 2 other terms come in. And these are around the geometry of screw dislocation. So what does it look like? What is the geometry of the step edge that you actually have that is trying to retreat? Here's exactly the same data, the temperature dependence of the dissolution rate, now cast into Patricia's framework. So we're taking that funny rate normalization of the rate here, over here, and that funny way of writing omega, and fitting lines to our data and finding these omega criticals in the Dove framework. In fact, one nice thing about the Dove framework, it really emphasizes where these omega criticals sit because of the big shifts that you see. And then we can go and then diagnose, right, what are those 3 main terms look like, and ask, is this theory working well? Right? And the answer is, yep, ish. And so I'll show you both the yep and the ish part. So here's what the information content of the intercept, and here's the information content of the slope of those systems, now plotted because we have the temperature dependence as 1 on t squared. So there are 3 or 4 points in here, depending on how many different temperatures we made the measurements. And you can see that there is a clear difference in the intercept, much lower here for those defect-assisted dissolution ones, as opposed to the homogeneous dissolution. So this is fundamentally the different frequency of etch pit formation showing up for the 2 different modes. Over here on the right, we could compare to the literature. What is the measured surface free energy for calcite in seawater? And it's very close to this number. And the theory is predicting a particular slope for a temperature dependence, and we're finding that slope or close to it in our experiments. Awesome. At very far from equilibrium, it looks like the theory is doing a good job of describing our seawater dependent dissolution rate of carbonates. Not so much for defect assisted. This is a very different surface free energy than what we think is the basic one for calcite and seawater, and it has the wrong slope of the temperature dependence compared to what the theory would predict. We noticed that. We talked about it in the paper. We didn't really understand. I think what's going on here is the chemical speciation piece of the problem that we're going to look into a little bit here in the next few minutes. Okay, before we get to the speciation, we were running into this problem that we were working on dissolution of solids and coming up with theories that are about the different shapes of the solids in a different energetic environment right at the solid surface, and doing it all from the aqueous side. Right? We were aqueous chemists putting a tracer in, looking at the concentration increase of the tracer in solution, and yet there's this whole world out there, a whole slice of the geochemistry meetings, of mineral physicists and dissolution rate experts who watch the evolution of the shape of the surface instead. You could argue about which is a more natural framework to be working in, but that's where the field was, and we weren't there. And so we said, let's try. Let's go do atomic force microscopy measurements and monitor the shape of the surface in the same kinds of experiments that we've been doing out in the bags in the lab. So that's what Sitcha figured out. And it was a really hard problem. No one had ever done AFM in seawater before, and these very important little probes dissolve like crazy in the seawater, and so you can only measure for like 20 minutes. I don't know if any of you do AFM measurements, but it can be quite finicky, especially if your probe is dissolving while you go. And it was an open system, and we needed to keep omega constant, and so Sitcha had to come up with a really beautiful way of a constant PCO2 in the headspace so that omega didn't evolve over the course of the experiment. Here's the kinds of things that you got. This is close to equilibrium, 12% undersaturated. Here's further from equilibrium, 50% undersaturated, crossing those omega criticals. Right? We're on a different side of omega critical. The shape of the surface over the first half an hour, I think you can see step edge retreat going on here at this point. Right? This is energetically the most favorable place if you're close to equilibrium for where the solids are going to come off. This is not a discovery. People had seen this kind of behavior lots before. And then farther from equilibrium, there's a bunch more noise here in it because our tip is dissolving. But over the course of 40 minutes, you can see that we go from very few etch bits to suddenly etch bits opening up and the etch bits expanding. We're able to go actually measure the etch bit size, the etch bit frequency, the step edge retreat rate. We can go compare from the solid side to some of these numbers that we've been diagnosing from the aqueous side. And so Sitcha did a bunch of different experiments, AFM experiments at different 1 minus omegas. Her data is here in blue as the seawater. I'll talk about the freshwater stuff in just a second. As you might imagine, these 3 different color bars that I put up here, these are the omega criticals that we diagnosed from the aqueous side. Right? So these are the ones that we said, here are the break-in slopes that the Dove framework is telling us we're changing modes. And indeed, if we're too close to equilibrium, we don't see any etch bits at all. Once we cross the defect-assisted threshold, omega of about 0.9, or a 1 minus omega of 0.1, we begin to see etch bits, and their density, right, their number per area goes up until we cross the final threshold, and then the nucleation rate is at its maximum number, and so the area stays constant even though we're getting more and more acidic. We loved this result, right? This is a very nice demonstration that if you look at it from the solid side or you look at it from the aqueous side, we're getting the same answer. Right? This Dove framework is turning out to be a really nice way to think about the kinetics. The surface energetics are clearly driving the bus. Honestly, it broke my heart. And it broke my heart because I'm a chemist, and everything I just told you about, a physicist would have been able to solve, right? Like, this is a theory that's just about the energetic balance at the surface, and the only reason the chemistry matters is to provide a delta G. And then the chemists are done. You guys got to kind of go home. We don't care how much it is calcium or how much is carbonate ion or ion pairing or all the sort of fun things that we care about as chemists. It was just an energetic argument. And yet, freshwater is somehow really, really different. Why did Arakaki and Mucci do such a good job as aqueous chemists of describing the fundamental rate law and never worry about this? Right? They never worried about the surface energetics at all. They were able to describe all of the data that was out there in the literature just with the classic way we wanted to do it when we got into this problem of elementary reactions. And that turns out to be a quirk of the energetics of calcite in seawater versus, and I think the speciation of seawater versus freshwater. In freshwater, that final omega critical is almost at infinitely undersaturated. And so all of the data collected in laboratories in the 70s and the 80s that Arakaki and Mucci were fitting had just one mode of surface energetics. And so it was invisible to them, these transitions. All they could see was the chemical kinetics part because they were always in the same mode. Is that luck? Is that like why? Is that like a rule in the universe? Why is it so different when you take exactly the same mineral, the calcite, and move to seawater? Well, that's got to be speciation. That's got to be something about all the other things that are going on in seawater besides being the exact same omega. Right? You can describe the undersaturation in the same way, and yet there's sodium and chloride and magnesium and all sorts of other sulfate around in seawater. That got us excited again. Right? Once we sort of realized this piece, it's back on the table that we could be chemists and not just physicists. And so, and this turns out is like really hard because the speciation in seawater is a really cool mess that is worth working on. I was talking to Emily about this morning. I think she's working on it from a quantum point of view. Unbelievable. I wouldn't have tried that. Seawater has all these other ions that are there. This one is especially important. There's 10 times more carbonate ion complexed as a magnesium ion pair in seawater compared to just the free carbonate ion that's out there. This is something that oceanographers have known about for a long time and figured out with empirical ways to come up with it, but the ion pairing, the speciation just on the aqueous side is important. But Van Capellen pointed out, right, about freshwater, you better understand the speciation at the mineral surface as well if you're going to get the right activities to plug into a rate law. And so we said, cool, we can go after this experimentally because we can make fake seawater. In fact, we had been doing this initially we were going down to the coast and collecting seawater in Pasadena. I don't know if you know this, is like an hour from any waves. So if you're a surfer, it's not a great place to live, even though you're in Los Angeles. And we just got kind of tired of going to the beach all the time to collect seawater, and then the seawater would be a little bit different. And so we started using Francois Morel's recipe for fake seawater called Aquil. But the nice thing about that is that you can change it. You can decide not to add any sulfate, for instance, and then go change the major ion ratios, the background electrolyte that we're all supposed to ignore right when we think about these problems, and ask, does it change the kinetics? And it did in this totally wild way. Here is a plot. It's the same idea now. This is a log linear one. Log of the rate over here on the left, but now a linear version of, oh, I'm sorry, this wasn't labeled, again, of the 1 minus omega. So you're close to equilibrium over here on the left and very far from equilibrium over here on the right. The green dots are the Navio data that I was showing you before at 21 degrees C, so sort of like our reference frame. And then John, and Holly, who's been working on this problem since, still in my lab, have done half sulfate and free, no sulfate whatsoever in the water. You can see very far from equilibrium, if you take sulfate away, the rate goes up. Sulfate is an inhibitor of the dissolution far from equilibrium. That was actually already known in the literature. People had done experiments like that. And the idea was pretty straightforward, right? That this sulfate is attaching to the surface and blocking attack, right, of the calcium-free site because sulfate is complexing calcium that's there. And so if you take the sulfate away, there's more free calcium, larger activity of one of your reactants, and the rate goes faster. But I played a trick on you, right? I showed you a blown up version of it. It was only here to 0.3. There's lots more data, right? These guys have been working really hard, close to equilibrium. Here's that same reference line, the green dots that you see here. The data that I just showed you before is sitting up over here. That's that acceleration of the rate when you take sulfate away. Close to equilibrium, when you take sulfate away, you go slower. The effect changes sign as a function of omega. Like that was like, come on, really? Like, I thought we were getting our head around this problem. Like we were actually beginning. And yet, I think this was a really important clue, and we're now still in the middle of this. The answer really seems to be, and people have done, and this is folks actually in thinking about the oil and gas industry and doing enhanced oil recovery from carbonate reservoirs. We're really worried about the speciation of carbonate under briny conditions. And they worked out carbonate ion binds to the surface much more strongly than sulfate does. And so when you're close to equilibrium, there's lots of carbonate ion around. When you're far from equilibrium, there's very little carbonate ion around. And so far from equilibrium, it's only about sulfate and the free surface, right? There's no carbonate ion to interfere with that competition. And so if you remove sulfate, you go faster. But close to equilibrium, sulfate could displace carbonate ion and then be easier to dissolve. Why would sulfate displace carbonate ion? It's orders of magnitude more concentrated in seawater than carbonate ion is. And so you have partitioned more sulfate to the surface. Even though it doesn't bind as strongly, its concentration side of that is so much higher that you have an appreciable amount of sulfate complexation and carbonate ion compensation. And if you take away the sulfate concentration, more carbonate ion goes to the surface, and you dissolve more slowly. John was able to initially quantify this. We're trying to cast it now into the Arakaki and Mucci framework. We actually think the fundamental rate law discovered in freshwater is actually operating in seawater. You just need to get the conditions right so that you can see it. You got to have one surface energetic mode. You got to go explore what the surface speciation is. We're still in the middle of working this out, but I have to say it's been really fun. Like this is like the whole point, right? Is you just keep scratching at the surface. Okay, why does any of this have to do with spinning out a company to go decarbonize shipping, right? That totally reasonable question you might be asking yourself and wondering why you just wasted the previous 40 minutes. I will try to bring it home here for us on how they're related. We're going to try to do this reaction, but fast enough to keep up with shipping. Remember these two problems, right? That were keeping AWL from being applied at a climate scale or industrial scale. The first one was you didn't understand the kinetics well enough, so you couldn't design chemical reactors. We just solved that. It took us 10 years, but it was like one of these aha moments, I'll describe in a second, of wait a minute, we're not working just on the basic science here. What if we tried to apply this somewhere? And then what I'm going to show you after a couple of slides on catalysis is how ships are actually a beautiful technological match because the ship is a giant water pump. And so unlike needing all this extra energy on land where you're going to have to pay for every single drop that you pump uphill, if you open up a hole in the hull of a ship, the displacement that it's already doing gets you a lot of the kinetic energy you need. Okay, so how did this actually happen? Like, why did we go from total like nerds in the lab noodling along, right, to saying, yes, we're going to go spin out a company to go take on a gigaton of CO2? It's because we discovered a catalyst. And it was the discovery that carbonic anhydrase accelerates the dissolution of calcium carbonate that was very exciting. And for 3 weeks, we were just talking about how it meant that this carbonic acid attack term was probably more important in seawater than it was in freshwater, and that's so interesting. And then getting ready to go coach my kid's soccer game, I was taking a shower and had this aha moment, like, wait a minute. We are making the reaction go faster. Right? We are making the Earth's planetary scale buffering reaction, CO2 plus calcium carbonate going to ions in solution, go 500 times faster close to equilibrium. Here's the lab data that Adam collected during his thesis. This is under saturation again, this 1 minus omega, now on a linear scale, versus the log of the dissolution rate. Here's the background, no carbonic anhydrase. And as you add different concentrations of carbonic anhydrase, near equilibrium, we have a 500-time increase in the dissolution rate. That was exciting. That was like, hey, wait a minute. Like, if we're making an important reaction go faster, what do we do? What do we do, right? And this is like, how many different mistakes can you make as an academic trying to think about spinning out a company? I jumped out of the shower and said, okay, we're going to try to sequester all 40 gigatons, it was like 38 gigatons of human emissions, right? That had happened the previous year, just with our reactor that we're going to go build with 2 miles squared of limestone. That's the stoichiometric equivalent that you would need to do all 40 gigatons. And we're going to build out Walmart superstore size factories, right, to go do this. No, notice there's no customer here, right? This is just like, hey, this is what we're going to go do, right? And if uncatalyzed, that's 24,000 Walmart superstores that you would need, and catalyzed, it's like 600. And so still like dripping wet from the shower, I had looked up what the size is of Walmart superstore, and then said, well, how many are there? It turns out there are like 3,000 or more, it changes, of course, day to day, in the US alone. And I thought, excellent. Those things are, stuff is coming in, stuff is going out, people, like there's a lot of activity in and around a superstore. 600 is a big number, but it's not a crazy number. Literally, no idea about a customer, no idea. We were like, yes, we should go make a company around this. And the first problem was, does it work when you start going build reactors? And so I took a little sabbatical in Will's lab at USC and started building reactors to test carbonic with and without carbonic anhydrase. So here's something on the lab bench in Will's lab. There's a little bottle bubbling CO2 into freshwater in this case. Let's see, I think. Yeah, there's a pump. There's into the reactor, out of the reactor. The cardboard box that this is sitting on is actually crucial to get the flow right. This is right. A very robust system I had built here. And indeed, as a function of flow rate and the outflow PCO2, this is uncatalyzed in blue. If you flow slowly, then you take up more of the CO2. It was on this axis, it was 50,000 is the value. It was 5% CO2 we were using. And if you flow faster, of course, you don't capture as much of the CO2 as you flow more water through. And if we added carbonic anhydrase, the whole thing got better. And if I wrote out a little set of differential equations to describe how that system would work in the uncatalyzed case, this is the dashed blue line. We already were doing a good job of predicting the lab data with the first principles use of our rate data from the lab. Another way to phrase this would just be over time. What is the carbon difference, outflow of the bottle, outflow and the bottle, and there's a lot more carbon catalyzed than there is uncatalyzed. But this is a adding the enzyme, very expensive, right, into the water in an open flow system. This is a terrible design for any industrial scale, right? We're going to be dumping tons of catalyst into the environment if we did this, and it's the most expensive thing by far in the system, right? We need to figure out how to bind the catalyst and keep it inside of the reactor. Okay, open up a project, make some decisions early on that we're going to go after either entrapment in silica gels that had been friends of ours at Livermore had been working on, or straight up binding it to silica glass beads through a linker. We didn't know anything about working with enzymes in the lab as inorganic chemical oceanographers. Hired a really terrific person in, and about a year and a half, year and 3/4 later, it worked. We were able to preserve about 80% of the activity of an enzyme bound to silica glass beads. Here's a picture of them either in mesh bags or in a little bit bottle. And in fact, it was even better, right? The binding it to the glass beads preserved the activity for longer than just keeping the enzyme in solution. It's a little bit delicate, just sitting there in seawater. And so John built these 2 different flow-through reactors, much like the ones I'd built at USC a few years earlier. And over the course of a number of hours, monitored the alkalinity on either side of the reactor, first just running them both the same, and then he added the beads to reactor number 2, and there was still no difference between the 2 reactors. That was very frustrating to John. He'd been trying this for years now to try and get the thing bound, and so he said, oh, and he just squirted in carbonic anhydrase, the dissolved form, into the reactor, and the catalysis jumps right up. Uh-oh, right? even though we're preserving the activity of the enzyme by binding it to the solid, when you put the solids in the solution, you lose the catalytic activity. Well, it turned out Sitcha figured this one out also by doing AFM in a parallel set of work, not thinking about the engineering side, but just trying to go after how does CA work fundamentally. She was running AFM experiments, but now adding carbonic anhydrase to her system, and she kind of made a mistake. She added so much that she made this flock. So this is, what you see here, this is carbonic anhydrase as imaged by an AFM, landing on the surface, but it's a flow-through system, and so it got ripped off after a few minutes, and look at all these etch bits. The reason carbonic anhydrase is catalytic is because it's sticking to the surface. And it's actually ripping a proton off of water in its active site and hydroxylating CO2. That's the process of which it actually works. And that proton is being expunged from the system, and half the time it goes and dissolves some of the solid. It is absolutely a catalyst in just the way we had discovered in the lab, but not for the same reason. We thought it increased the activity of carbonic acid. That's not what it's doing. What it's doing is actually changing the activity of protons right at the surface. That's not going to work in our reactors. We're not going to get the enzyme to hop on and off a gazillion little grains in a reactor that is a 10 or 15-minute residence time of water flowing through. Total solar plexus shot for the company. Right? However, at that point, we had gotten better, right? This is the big bummer, at thinking about a customer. And this is where we had really begun to focus in on shipping. And it's because ships are little floating power plants with 5% by volume CO2 in their exhaust, which means that even without the catalyst, they make seawater acidic enough to dissolve calcium carbonate fast enough to keep up with a significant percentage of their CO2. In parallel, we had realized that. Realizing the catalyst wasn't going to work sort of accelerated our thinking around that. And like I said before, the ship's forward motion is a giant water pump. We've got both of the two hurdles solved in AWL with shipping. On the commercialization side, right, there are a few things that the ship owners really like about us. Our system doesn't have to offload anything in port. If you were to build an onboard carbon capture system that used amines or something like that, you're still trapping CO2 at sea and need to go offload it in port. We're doing capture and storage all at once. That's the second point. And we don't have any intermediate purification, pressurization, or refrigeration. Right? We're going to be much cheaper than the way that you think about carbon capture on land at giant power plants. You think about these as huge CapEx problems, like $100 million plants on huge coal-fired power plants, right, in the center of the country. That's not what's going to happen with shipping, right? There are 50,000 of these little power plants all zooming around the ocean. It's going to be CapEx much less intensive than those things. Okay. So excellent. What do we do about that? We started building reactors in the lab that we thought might work with shipping. The idea here is that there's a gas absorber and then a stirred tank, and then we went and built 4 of them. These are working in series. Go collect a bunch of data, so over the course of a couple of hours, collect alkalinity, pH, PCO2 in all 4 of those channels. And again, the models here are the lines, and the data are the X's. And so this is, we haven't used any sort of fundamental upscaling here. We've just used our first principles understanding of gas exchange and our first principles understanding of the kinetics to be able to write out these laws, and we're doing a good job of getting the right number. So we started building much bigger things. Our first prototype that we landed in January 2023, I'll show you a picture in a second, at a parking lot in USC, was a fluidized bed reactor because we hadn't talked to any customers yet, and we were worried about space. We had decided we understood what the problem was ahead of time and said the biggest problem on a ship is going to be taking up their space. A fluidized bed reactor where you have all 3 phases interacting at once, the gas, the solid, and the seawater, is the smallest area that we could compress our system into. I'll show you why that turned out to work, but not to be the best. And we have moved now to systems that separate the gas absorption part from the solid dissolution part. This is a classic exhaust gas capture system of a shower of water and a counterflow of gas, and then packed beds of limestone that receive the acidic water from below and flow out the top. When we do this, of course, we can measure in and out in real time. We've developed an optical sensor that measures pH, alkalinity, and DIC as a whole separate piece of the company. And so our verification, right, our count 'em up of the number of atoms is a measurement, not a model. That's a big advantage compared to a bunch of other ocean solutions. So there's our first fluidized bed reactor in January of 2023 in a parking lot in USC. That's a diesel generator about the size of an F-250 pickup here on the left. And here's the fluidized bed over here on the right, a bunch of pumps and cooling and things in the way. And when we go and run this system, there's about 6.5% CO2 in the exhaust of that diesel generator at the way that we were running it. Before you do anything, turn a bunch of valves, and we only have one CO2 sensor, so you run over and stick it above the fluidized bed reactor, and we're taking up about 30% of the CO2 from the gas stream. Here's our model of how much we thought we would take up in the blue line. We're not getting these little deviations because this is us lifting up the lid to take water samples as we go, and I didn't try to model that part. But we're getting the right number. Yet again, this is now close to 100,000 times bigger than anything we built before. No fudge factors, right, in the equations for scale up. Here's an engineering kind of fudge factor. But we're not making very much alkalinity when we do that. So alkalinity versus DIC, this is the sort of equation of state for seawater inorganic chemistry, contouring pH. Once you know these two, alkalinity and DIC, you can calculate anything else, pH, carbonate ion, PCO2. So isolines of pH that you see here are starting water in one experiment over on the left, starting water in another experiment here that's circled. And when we use big grains, we capture a bunch of CO2, but we don't convert very much of it to bicarbonate. We don't make very much alkalinity. If we drop the grain size by an order of magnitude, now this slope is much more tilted. We're adding a lot more alkalinity as we add the DIC, but this is a non-starter. All of these grains flow out of our system as we're going along. They're too small to actually stay behind. We had begun talking to customers at this point, and they also didn't like the idea of carrying around these columns of water everywhere that were potentially sloshing around. And so we shifted to building a gas absorber and splitting the flow into multiple packed beds. If this looks like we're brewing beer at the Port of LA, it's because these are bought from the microbrewery industry. We kind of got better as a startup. Rather than build a $1.1 million prototype straight out the bat like we did, this is faster, better, cheaper of buying some off-the-shelf equipment and then converting it into what we need. So this system is going to do gas absorption separate from the solid dissolution rather than doing them all at once. So here now we've run for a few hours, alkalinity, DIC, pH. Over here is probably the best place to start with a 5% PCO2 coming in. And as we come to steady state, now we're doing about half of the CO2 that's coming out of the system. And we're making a whole bunch of alkalinity. Again, lines are the model, circles are the data. If we look at this now in that same space of alkalinity versus DIC, now we can take data coming out of the gas absorber and data coming out of the full system after you've gone through the packed beds. Here's the starting seawater, and the gas absorber adds carbon but doesn't change alkalinity at all. CO2 doesn't change the alkalinity of the system in any way. And then we go to the packed beds, and this is a slope of 2 to 1, just what you would think for the dissolution of calcium carbonate. And indeed, now we're converting about 2/3 of the CO2 that we trap in the water is becoming bicarbonate. It's a much, much more efficient system that we think we might be able to build out at scale. And so what does that look like? These are the last couple of slides. Here's here's the absorber part and the limestone beds fitting just in a first cargo hold just in front of the engine room of a very, very long ship. This is a 300-meter long ship that you see here. These percentages are how much of the total parasitic load is going to hydrodynamic drag or to compressing the gas that you see. Our total parasitic load is about 15% of the fuel, or 15% fuel penalty. In net, this is 53% of the CO2 being emitted by this Panamax-sized vessel on a 14-day trip. We're doing a big chunk of its emissions. We're not doing 100%, but it turns out we're doing economically enough to save them money, and I'll show you that here. So you go build out a techno-economic analysis, and like now, like we're actually starting a little bit more to sound like a company or sound like engineers, right? Learning along the way. Here are all our costs. Here's how we think we could save the money. There's a very big difference between these two bars, is one of the main points of this graph, right? Why is there such a big difference between those? We're about 480 kilowatt hours per ton of CO2 sequestered and of captured and stored. That's something to keep in mind, right? That we're talking not just about the carbon capture part here, we're talking about an integrated piece that has storage as well. And overall, we come out at about $99 a ton. Happy to talk through that more with folks. You go build out a team. This is the best part about starting a company, is that you literally are nothing the day before you actually spin out, and then there's a thing 3 years later that's like this big machine that's actually working on stuff. I love this part of starting companies, or the one that we tried. This is my last slide, and it is chapter 2 of Calcarea. We think there's a route towards using using ships and using these reactors on specially built ships that now don't carry sneakers or televisions or oil, right? They only pick up limestone and CO2 in port, and you compete with storing underground. We think that we can go to scale and be less expensive than having to make a supercritical fluid and transport carbon to a hole in the ground from wherever it was captured, and do a better job of sequestering CO2, including a big change in the infrastructure that you would need to be able to transport CO2 instead of the holes in the ground into the ports. This also frees carbon sequestration from being just controlled by the fossil fuel industry, right? It puts it into the hands of much nicer, better looking folks like us. That's a company that we're really looking forward to building. Thanks very much. I'm happy to take any questions that you might have.
So I think there are microphones around for anyone who wants to ask a question.
I'm sorry I stopped right at 1:30, and I know that means that folks have to go. That's perfectly fine by me. Hi, Lynn.
Yes. Wonderful talk.
Thank you.
I wanted to ask about the regulatory hurdles.
Yeah.
We talked about that.
Yes.
On the technology side, how much calcium carbonate are you going to have to carry on the ship? For a 53% capture, let's say the vessel, transatlantic, 40 days, how much do you have to carry?
Yeah, everyone picks 40 days. We picked 15, but it was 3,000 tons of limestone on that TEA that was there on a 63,000 DWT ship. And so if you want to go longer, we have to carry a little bit more. And so the answer is a little variable. It's about 3 to 5% of the cargo space. That was one of the bars on our costs. It was the smallest one. It's fourth on the list, the lost revenue from the cargo space that we take up on a retrofit model. On a new build model, you just make a slightly longer ship, and we don't have to take up any extra room. I understand that that's kind of a glib comment. And then the other piece of this is we carry much more limestone than you need stoichiometrically to deal with the CO2 for that next voyage. And that's for two reasons, a chemical engineering one and an operations and business one. The chemical engineering one is there are two potential rate limiting steps. They're the mass transfers. The mass transfer of CO2 from the gas phase into the water phase, right? That's the gas absorber. And then there's also the dissolution rate in the packed beds, the transfer from the solid into the solution. The second is much slower. And so we need more surface area. And so we carry, and so the grain size distribution matters to us, and the total amount matters to us to have enough surface area so that we get to that 2/3 number. So that something like well over half of the CO2 that we capture into the water is actually being converted into bicarbonate. That's the chemical engineering reason. The operation reason is that now means that we could skip a port call. We load as a slurry directly into the packed bed, so there's no hoppers on board, or we don't have to move solid around once the slurry loads in. But we could not load for a port call or two. You'll be less efficient on leg 2 and then definitely on leg 3, but you would still be doing enough to save yourself a fair bit against your carbon tax. And it might help a lot operationally for where it is that you're in the world or how much the limestone costs at that particular place. There's a really interesting optimization problem around that we haven't done yet.
But how much does that change the operations, like the residents' time and things like this? Because, I mean, your packed bed is being depleted as we go.
That's right. This is a non-steady state process. And so we often, that 480 kilowatt hour per ton number changes if you change the speed of the ship or if you change the length of the voyage, right? And this becomes hard to compare apples and apples, right, with us. Yes, it is a steady state for the gas absorption, non-steady state for the solid dissolution. We dissolve about 15 to 20% of the total limestone that we carry on each voyage.
But you measure you measure that amount of carbon dioxide removal continuously, so you know after the fact how much you removed.
Absolutely.
Yeah.
Yeah, we know in real time how much we've removed because of the measuring the triplicate of alk, D, IC, and pH. And so there's absolutely an operational piece of building this out at ports of how you're going to do limestone handling. We think that that is much less expensive. We've costed it out and intrusive than having to offload carbon at port. Great questions. Yes, in back.
Yeah, this is kind of piggybacking off the last question.
Sure.
What kind of particle size of the limestone do you actually get from that?
In that TEA, that was a particle size distribution centered around 700 microns. We've looked at the cost curve of limestone as a function of grain size, and it turns up very expensive below about 100 microns. But that's not the only piece. It's not a continuous thing. It's discretized because different slices of the industry, like toothpaste versus paint versus cement, want different sizes of limestone. And so the grain size can matter in that sense. Are you competing with toothpaste? Then it's going to get more expensive. Are you in between and it's just a byproduct that they don't know what to do with? We get it very, very cheaply. So there are interesting dynamics around the limestone price. But roughly, if you go below 100 microns, the price is going to get really hard.
Take the precipitate that comes from our process.
Yeah, so we're happy to take other sources of carbonate, especially if there's a worry about how green it is. Like we'll greenify it. That's a totally made-up word.
Thank you very much, and thanks to
everybody.
Jess.
I appreciate you staying.